Well, welcome back. Chapter 2. Now we're getting real close to some of that calculus you've been waiting for all this time. Especially some of you that already know some of the shortcuts. We're not quite there, so hang in there, but we're getting there. So limits. I just thought this picture looked nice. If you see a better picture than want to send it to me, fine, but I'm not going to change the video. Okay, so left and right hand limits. That's how we start talking about limits. That way we get a feel for it. And then we want to know what is a limit or the limit of a function as x approaches some real number a. Not infinity, a real number. Before we go any further, I'm going to grab a pen here, so this will be part of the recording. There's my red pen, and let's check it out here. Okay, we're ready to roll. Next, we've got left-hand limits, right-hand limits, and value of x if they both come to the same place, then we've got a limit. Value of f of x at x equals a in a polynomial, and x is the value of a, gives you a function value of f of a. And if x is approaching a, then f of a has some value. You're probably approaching that, although that's only in the good case. You have some unusual ones too. So left-hand limits, right-hand limits, x approaching some number, we're just calling it a here. The left-hand limit means as you're traveling along the function, like as if you were bicycling or walking or something, you're getting close to a, which is some number. You want to know what height or what y value you're actually approaching. From the right-hand side, that's coming from the right toward the left, toward x equals a. What is your y value getting close to? It might or might not be the same as from the left-hand side. And one of them might not even exist. But we're starting with something relatively simple with coming from the left or coming from the right. So left-hand limits. So we're talking, the limit is talking about values of f, alias f of x. When x gets close to something, x gets close to a from the left, remember we're sliding along that curve, or straight line, whatever it is for the function. As we get closer and closer to a without getting there, what does the function value get closer and closer to? If we have a limit, that means the limit of f of x, that's our function, and x arrow a with a minus sign up there means if you took the value of a, whatever that number is, and just shaved off a real tiny amount, x is approaching those values. But it isn't actually getting to a, it's getting closer and closer and closer until you need an electron microscope to see how close it is, but not there. What we're saying is if it approaches from the left, that's what this means, that the y value is getting close to what? Well, we're just using k for that one. Some places say y approaches L, excuse me, because L for limit. Here's a picture, and remember, we're on this function, we're starting from the left, and we're getting close to some value. So if we look at this, we're talking about what happens as x approaches 0. So here we are. Sorry about the stick figure, I'm not that good. And we're heading in that direction. Left-hand limit means we're coming from the left towards some value. And this is going to be our x value that we're getting close to. In this case, what happens as we're running along here, or walking along here, or bicycling along here, where are the y values when we get really close to 0? Well, as I get closer and closer here, at the very beginning, the y value is a -1. See that -1 there? As I get closer, notice when I'm here, y value is still -1. When I get closer, y value is still -1. Even when I get very, very close to x equals 0, the y value is -1. So the limit of this function, call it f of x, or you can call it y, and x is approaching 0 in this case, and it's approaching it from the left-hand side. So if you take 0, slice off just a small bit of it as if you're in the deli. So maybe you're up to -0.00015 or something like that. Getting very close up here to the x being 0. What is the y value the closer you get to that x equals 0? Well, it's -1 all the way. So the limit as x approaches from the left is -1. If I approach it from the other side, we're going to still talk about x equals 0. What happens if now you're here, there you are, and you're headed toward the left, but from the right. So now you're talking about the limit as x approaches 0, but there are tiny values just to the right of 0. What is the y value as the x gets closer to 0 from the right? Well, you're here, the y value is still 0. Get over here, the y value is still 0. Here, the y value is still 0. See? 0. So the limit, it never gets anything except 0, so that's the limit. Now if it flipped over that 0, but we're not allowed to do that, so we're not even going to talk about it. Up here, this is a little bit of a different story. By the way, notice this is actually what our function is. It's y equals, and you know what this is? That means it's the greatest integer function. Greatest integer function looks like this, and what it means is the last number before or at you get to x. 3 quick examples. First of all, if you have the greatest integer of 5, think of it as creeping up on 5. What's the last integer you hit as you hit 5? Well, you've gotten to 5, so it's a 5. What about the greatest integer of 0? That's 0. Remember, you're coming at it from this side. What's the last integer you hit? So let's try something else. What if we have 7.3. So if we're running across the number line from left to right as usual, and we get 7.3. 7.3 is not an integer. What was the last integer we tripped on before we got to 7.3? Well, the last integer we saw was a 7. So there's the greatest integer. Take a second one. Let's suppose we have 13.9. Now that's pretty close to 14, but if we're coming from left to right on the number line, what's the last integer we hit? 13. Now, from the other side, suppose we had the greatest integer and we put a -3 there. Now, as we're coming up to -3 and hit -3, -3 is an integer, so there's a -3. What about a little bit different? What if it's -5.7? Now things get a little bit more interesting. Because over here with the positive numbers, it almost looks like when you want the greatest integer, you just throw away the decimal part. But that's not quite true. Think of it as walking along the number line and from left to right until you get to 7.3. What was the last integer you saw? 7. Last integer before you got to up to 13.9. You never got to 14, so it's still a 13. Now this one, you hit -3, that's already an integer. Bingo, you got it. Now if we're coming from the left, picture the number line. The last integer you actually got to was the -6, because the -5.7 is to the right of that. And you haven't got the -5 yet. Another one, let's suppose we've got -13 let's say 4. So start from the left, somewhere to the left of that number, and sneak up on -13.4. Well, -13.4 is not an integer, so that's not your answer. What, as you crept up on from the left, what was the last integer you saw? Well, it would be -14. If you're not familiar with this, play with it a little bit. You could even test it on your calculator. Your calculator does have a greatest integer function. Probably, if you've got a TI-84, for example, it's probably under the math series of functions. So that's a little bit about the left-hand limits. Now, how about the right-hand limits? That means we're on the right of some number. Remember, we're talking about x's first, and then we talk about the y values next. So if you're getting close to something, and here's our graph, and maybe here is a number we're getting close to. If it's a right-hand limit, that means we're coming this direction, and we're looking to see what the function value is when we get close to x values that are almost a. As you sneak up on this x equals a, where is the y value? Notice how this is described symbolically. It's the limit of f of x alias y. As x gets close to a, and this means it gets close to a from the right-hand side. And this says, as it gets close to a, that the y value gets closer and closer and closer to some number m. So let's take a look at this. We've got a graph to play with. Here's our function. Call that f of x. I think that looks good. Let's see f of x there, but We'll assume it's f of x. So, left limit. And we're going to talk about approaching this 4. Now, if it's a left limit, we're approaching it from the left side, which means the only x values we're going to see are values just a little bit less than 4. So we'll start up here. Here we are. And we're traveling along this function. We're going to start here, we're going to keep on going, and we're going to get as close as we can to 4. But limits mean we're not actually getting there. We're just getting real close. And as we get real close to x equals 4, what's the y value of it? How far is it above there? Well, as I walk along this, I go down, I go up a little bit. As I get very, very close, notice what I'm getting close to is 6. 6 units above the x-axis. That's the left limit. So the limit as x approaches 4 from the left of our function is, and notice that as I get close, it's a little bit bigger than 6. It gets closer and closer and closer to 6. From the right side, I know it says right-hand limits in here. We're doing the whole thing. So this time, let's see if I can change this color. Oops. Oh, there we go. I'm going to pick up a different color and see if this will work for me. I'm going to pick up a green here and see what happens. All right. So this time, I'm on the right-hand side, and here I am, and I'm headed from the right toward where x equals a 4. As I do, notice that over here, see the cursor? Right here, I've got a value of 3 for y, or my function. When I get down to here, it's about 2. When I get down to here, it's almost down to 1, but it isn't. Maybe 1.2, 1.3, something like that. And we're always talking about the y values. But when I get past this point right here, the y values start getting bigger. And as I get very, very close to x being equal to 4 from the right side, the value of y gets extremely close to 2. So you can write that as the limit. This time as x approaches 4, but from the right this time, notice the plus and the minus. There's a minus, means left. Plus means on the right. We're talking about the same function, maybe a little bit of a strange function, but all of us are a little bit strange, right, in our own way. What does it get close to? Well, it was up here at about 3, dropped down to about 2, dropped down almost to 1, but then it rose up and it was approaching or getting close to the y value of 2. So the limit from the right as x approached to 4 on the right is a 2. Got that? Okay. So let's take a look at this one. You can see that we've got a piecewise function, and over here on the right with the graph, you can see why it's called a piecewise function. You got 3 different pieces and they definitely look different. The first piece here is some kind of a curve, maybe a parabola. Hey, don't sneak a look back there, you know it's a parabola from that. On this section right here, you've got a constant function. And up here we've got a linear function. So it says, find the following one-sided limits by inspecting the graph. So let's see what it's asking for, and we'll put the picture above here. So first of all, we want to work on this one. I'm going to go back to the red to make sure you can see that pretty easily. And there's a dark red. Go with that. Alright. So we're talking about f of x. This whole thing is about f of x. So good. That graph. Second thing, what is x getting close to? X is getting close to 2. So we're talking about things real close to there. Now it says 2 with a minus sign up there, which means it's a left limit. So on this one, we're getting close to 2, but we're coming from this direction. So if we're walking along this one, here we are. And we're coming in this direction. We're following that curve. When it gets close to 2, what is the y value of those? What is the y value getting close to as the x is getting close to 2? So back here where we started walking, the y value is 0. When I got over this far, the y value is a 1. Keep going. We're not to 2 yet, but the y value is up to 2. We get a little bit further, the y value is up to 3. And as I get very, very close to a 4, get close to the 2, the y value gets real close to 4. So our limit from the left is a 4. Now, the second one says, how about x approaching from the right? So this time, we're still looking at getting close to this, but we're coming in this direction. And right here, the function is a line. We're approaching from the right. So here we are this time. And we're coming in that direction toward the 2. From the right. What are the y values getting close to when I move closer and closer to this x value of 2? Well, the y value, the whole way really, is a 2. No matter whether I'm back here, or closer and closer and closer, all of those y values are 2. And we don't care what it actually is here. What we're caring about is, what does the y value get close to as you creep up on that x, almost to x equals 2? What's a 2? So there's our right-hand limit. Notice the 2 aren't the same, even though in both cases we're approaching 2, but we're approaching it from different sides. Next. In this case, we're still talking about f of x, this piecewise function. This time, we're approaching 4. And notice we're approaching it from the left. So here is x equals 4. We're approaching it from the left, which means we're coming, I guess I need a different color. Sorry about that. Let's go back to the green, maybe. Pink color. Let's pick a green, see if this will show up. So on this one right here is our green. I'm approaching 4, which means I'm getting close to that. I'm coming from the left because of that minus sign. So I'm walking along here. This is me now. And I'm getting closer and closer to x being almost a 4 value. But everywhere along there, what is that? Is the y equal to? It's always a 2. So the limit as I approach 4 from the left-hand side is a 2. That's the only thing it is as I approach 4. And there are 3 answers, sorry. Next, let's look at 2 more from that same graph, that same function. On this one, I'm going to go back to red. Switch back to red. Okay. Now what are we doing? We're getting close to 4, but we're getting close to 4 from the right side. So 4 is our target, because we're coming in from this direction. This is our function coming toward 4. So here we are, we're coming in this direction. Here we are, we're in search of something close to 4. So moving down this way, that's toward the right x-wise. So I'm coming from the 6 and getting closer and closer to 4. What happens? Well, up here, the y value is 6. This is about 5.7, 5.5, 5.2. I'm down to a y value of 3. Oops, 5. And I still haven't gotten close enough to 4. I can get closer. So I get closer and closer. As I get very, very close, sneak up on this x value of 4, but not hitting it. As I get close to it, the y value, which is what the limit refers to, the y value gets closer and closer to a 4. Never quite hits it, because we're only approaching it. We're not actually getting there. So our limit of f of x, our function, as x approaches 4 from the right, is a 4. Started out at 6, got closer and closer, smaller and smaller y values, until we got very, very close to a 4. We don't care about actually hitting it. It's all about what we're getting close to. Part E. See what we've got here. We're talking about 0 this time. So our x value is coming close to the origin. Or, excuse me, x equals 0, which is the y-axis. So we're coming from the right. So now we're starting up here. Here we are. And we're coming in this direction because we're on this curve. And this is our function. And those are our ordered pairs. What is happening to the y values as I get really close to where x does equal 0. I'm not touching it, just getting close. As I do, going down to 4, I hit a y value of 3, and 2, and 1, and half, 1/4, and so on. I'm not going there at x equals 0. I'm getting very, very, very close. What's it getting close to as a y value? 0. Here's your limit. As x approaches 0 from the right of our function f of x. Next, here's our 2 answers. Looks as though we got them right. Well, they got them right, because we know we can get it right. All right, now, when it comes to limits, polynomial functions are our heroes, maybe, because polynomials are always smooth curves. They could do some unusual ups and downs and so on, but they're always smooth curves, and there are no gaps, no sharp turns, none of that nonsense. Like I said, they're fantastic when it comes to functions. So here are some things to remember. A polynomial function looks like this. These a sub n, and so on are nothing but coefficients, like a 5, a 16, maybe some fraction, and at the end is just one more. So this, for example, could be a 17 or a 17.85. All these a's are just numbers that you already know if someone gives you the polynomial function. They're all real numbers. The exponents, notice they're integers, and they're non-negative. Non-negatives, excuse me, you can't have zero. Zero is legal for the exponents. The domain, this is where this is really your friend. The domain is all real numbers. No restrictions whatsoever on what x can represent as far as a real number. Domain is all real numbers. Remember, that's for polynomial functions. Are the following functions polynomials? Now look at the first one. Is it a polynomial? Does it look like this with certain numbers thrown here, 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 and here, and so on? Now look at it. If you want to, you can put these in order. It's not important that you do. If we look at the coefficients, they're real numbers. Check. Are the exponents integers? Check. So this is a polynomial. And it's not only a polynomial, but you immediately know that the domain is all real numbers because the polynomial looks like this. What I would suggest to remind yourself what polynomial functions are is write a bunch of them down. Here's an example, but probably if it were me, I would put these in order. If you're ADHD or something like that, it might bother you to write it down like this. So put this one first, second, third, fourth, and it'll look nice to you. Let's go over here to G. G is another function. Remember, G just means that's the name of the function. So we've got 2, we've got 4, we've got 1, and we've got a -2. So it passes one test. All the coefficients are real numbers, but the exponents are not all integers. The exponent here is a 2. Check. The exponent here is a 1. Check. The exponent here is x to 0, which is 1. Check. But this one, if you remember, this can be written as x to the 1/2 power. And 1/2 is definitely not an integer. So this is not a polynomial. Function h. Well, before you do anything, you probably would want to multiply this out. 2x cubed times this, you've got the distributive property you need. So 2x cubed times this, the 8x to the 8th, we'll practice there. And 6x to the 4th, take a look at that. Just to pass all those tests. Okay. Real numbers here for coefficients. You've got non-negative integers for exponents. Bingo, you got it. And the domain is all real numbers, just as it is for all polynomials. Last of all, we've got a small problem here. Right off the bat, you can tell this is not a polynomial. You can't write it like this. If you wrote it even approaching that, you'd still have these things, these exponents, or these variables, excuse me, in the denominator. This is not polynomial. Polynomial should look like this. Next. There are your answers. They got it right. One-sided limits. Alright, so we've gone over this pretty well, I think. So just as a review, we're talking about a limit of a function called p. Notice that we're talking about polynomial functions. P of x is a polynomial. And that means you can say hooray any day you like. What's the limit of that function as x approaches from the left? Well, the good thing is all you have to do is take this number, put it in for x, evaluate that function at a, whether it's 6 or 9 or negative 52, whatever it is, put it in for p of x, and that is your limit. Another great reason why you like polynomial functions. Even from the right, the same thing applies. Since this is a polynomial function, then you can just take this number right here, put it into x, there's your p of a, and it is also your limit. Next, we've got a polynomial function. Notice this is a nice polynomial function. And let's see what we can do with that. Let's see if I can copy that. Let's see. I might do this in two parts. X cubed minus 4x squared minus x plus 10. Okay, there's our function, and we want to find some limits. Now, take a look at this. Is it a polynomial? Yes, it's a polynomial. So if I want the limit as x approaches 3 from the left, but since this is a polynomial, it doesn't matter whether it's from the right or left. All I have to do is take that 3 and put it in for the x's and evaluate it, and I'll have the limit. So the limit as x approaches 3 from the left of x squared plus 3x minus 7. I'll just put that 3 in where the x squared is, that's a 9. Put 3 in where the x is here, another 9, minus 7, so 18 minus 7, the limit for the first one is 11. This one, we want the limit as x approaches 2 from the right, and this is a polynomial again, so I want x cubed minus 5x. Because it's a polynomial, even whether it's the right or the left limit, I can just take this 2, put it in where the x's are, and get my limit. 2 in for the first x, giving 2 cubed, minus, and then we've got 5 times that 2 again, 2 in for the x's from here, and what do we have? 8 minus 10, our limit is negative 2. Negative 2 there, and let's see, that was an 11, and last of all, this is a polynomial, so it's easy. I'll just put 0 where the x's are, and what do I get? Well, the third one actually is the easiest. because when I put 0 in for these x's, these two terms are both zeros. What's left? The limit is 3. From the left, even if we had it from the right, it would still be 3, because we put the 0 in where the x's are. Next, the answers, and our answers are in good shape. Some notes: if a limit is supposed to be plus infinity or negative infinity, remember, we talk about if the limit goes positive without bound or negative without bound, then we don't have a limit, period. These symbols only mean that it's unbounded. Remember, there is no such number as infinity or negative infinity. It only points you in a certain direction. It's like you asking someone, well, how do I get to Greenville? And they point you in a certain direction. They don't tell you where Greenville is. You don't know how far it is. You just know, go in that direction. East, west, whatever it is. So here's a little bit about unbounded one-sided limits. The first one is about positive infinity limits. In other words, the number keeps getting bigger and bigger and bigger in a positive direction. We've got some pictures coming up. This means that x is approaching some a value, whatever that a value is, from the left. And this means as x is getting close to this, the y values are getting bigger and bigger and bigger, but in a positive direction. On this one, it says as we approach from the right, the y values are getting very, very big, again in a positive direction. So here's an example. Here's our a. If this is us, and we're headed along this curve, what happens as we get closer and closer to A? Well, as we get closer and closer, the y values get bigger and bigger and bigger and bigger, but in a positive direction, as opposed to going down this way. It would be a negative direction. On this side, as we are traveling along here, as we're going in this direction, the y values are getting bigger and bigger and bigger, again, in a positive direction. So we're heading toward positive infinity, which we won't get to, remember that. We're just heading in that direction. And it's pretty much the same thing for negative infinity limits, except we're going in the other direction. In this one, notice that we're coming from the left, going this way, which means we're going along the curve. What's happening to the y values? The closer we get to x values of a, well, the numbers for y are getting not only negative, but very, very big negative numbers. So that's what we mean when we say the limit is negative infinity. Because you've got negative numbers, the closer you get, and they're much bigger as you get closer to A. The other one is just coming from the right-hand side, and the same thing is happening. Further down you go, oops, it doesn't actually touch, but the y values continue to get larger and larger, but negative. One-sided limits. So what we have here is we're approaching, notice, we're approaching -3 from the left side. So where's -3? -3 is back here. And we want to find out, see, I don't know if this one should be here. This looks a bit strange. Anyway, so how does this work? We're approaching -3. Now what happens, one of the great things about polynomials is you just put the -3 in where the x's are, and you've got the limit. But what happens if I do it with this one? Well, -3 plus 5 is a 2, and that's okay. And on the bottom, -3 plus 3 is a 0, and your calculator's going to complain. That's called an indeterminate form because it actually can't get there because this thing, whatever you think of it as, doesn't exist. So what you'll have to do is sort of play with this. Now notice it's approaching from the left. So take your calculator, perfect example for using a calculator. We're talking about a fraction where the x values are getting close to -3. So it says we're approaching it from the left. So that means we don't quite get the -3. So one possible value of x would be -3.1. Yeah. -3.1 is to the left of -3. So what does it look like if we put a -3.1 in? If we put the -3.1 here, we get 1.9. Suppose we get a little bit closer, make it -3.01. What happens then? Put a -3.01 here, and we get 1.99. Let's try getting closer. -3.001. Put that number in here. Put the -3.001 in and add it to the 5. What do you get for y? You get 1.999. Can you see what's happening? As it gets closer to this -3, this rational expression has y approaching what? It's approaching a 2. Just play around with it, you get a feel for it after a while. No, you don't have to do that all in your head. Write it down. Don't try to be a hero. There, that's sort of what we did. Play with it. We've got a problem there, but see, that's slide 29. I'll make a note of that so I can fix it. All right. All right. Looks like I made a mistake, didn't I? In the positive direction, what happens? So again, it's approaching -3, but from the other side. So let's approach it from the other side. It's somewhat close. -2.99. If you're approaching it from the right side, what's the y value if you got -2.99? Add the 2.99 to the 5. What do you get? That's almost 3, so 2.01 over, then 3 plus that would be a -0.01. And what happens to that? You get a negative, oops, yeah, positive divided by negative, you get a negative, And 2.01 divided by this makes it actually bigger, 201. You get a little bit closer. What if we have an x equals negative 2.999? What do you get for the fraction? On the top, you get 2.001. On the bottom, you get negative 0.001. What's that give you? Again, you get a negative number, but this time it's 2001. You might also try one step closer, just to see for sure what's going on. You get closer to negative 3 from the right. What do you get? Try that for yourself. You might see the pattern already. It's getting very big. So what does that mean? First of all, it's negative. And the number is getting bigger and bigger and bigger. In fact, if you get much closer to that, you're going to see some very, very large numbers, even if you don't think 20,001 is a big number. Negative infinity. Okay. Fix that later. Positive infinity in one direction, negative infinity in the other direction. So let's take a look at the graph for f(x) and find the following one-sided limits. So we're approaching 2 from the left on this one. Here's 2. And we're coming from the left, so we're coming in this direction. So we're on this curve, and we're heading this direction. As we get close to 2, what's happening to the y values? We go from 1 to 2, 4, it's getting bigger and bigger and bigger. If you took this further, you can see that you're going to get just larger and larger and larger y values. So from the left, it approaches positive infinity because it's going up. On the other side, what's happening? You're approaching 2, but from this direction, and when you get anywhere close to it, you're somewhere like this. You're sneaking up on 2, but you're not allowed to touch 2. What's happening to the y values? Well, the y values are all the same. They're all 3s. So here y is 3, here y is 3, here y is 3. Even when you get very, very, very close, y is still a 3. Easy answer. Positive infinity, 3. What about 4? I'm going to let you go through these by yourself. You should have a pretty good idea what's going on. You should end up with 3s. You can come back here, or you can look at the PowerPoint later. Work it out for yourself. Limit defined informally, so you get a feel for what's going on. If the values of x, remember that's a y, if the y values get closer and closer to some number L, as the values are smaller than some number, in other words, from the left, getting close to t, and the values of x are larger, coming from the right, and getting closer to that same t that we talked about up here. If they both get close to L, then L is the limit as x approaches t. Notice that the limit, limit from the left exists. You can actually put a number to it. and the limit on the right exists, it means you can put a number on it. And if these two limits that you found are the same, then we've got a limit. Now, before we leave this slide, remember, saying the limit exists means there is a number. Now, does not mean positive or negative infinity. Those are not limits. That just tells you what happens to the function. For a limit to exist, there has to be a number that you can actually see on the number line. Same thing from the other side. And if those two match up, then you've got a limit overall. And this is one way of putting it. You've got the left-hand limit is something. The right-hand limit is some number. And if not only that, if they're the same, then we've got a limit. Hooray! So we can summarize some of this. Say the limit as x approaches the number t, and your x is approaching t. It exists if there's some number that exists for both the right-hand limit and the left-hand limit, and they're the same. If any of those approaches positive or negative infinity, then we do not have a limit. End of story. So what's happening here in the first one? We're talking about x approaching 3. So take a look at the picture. Where's 3? 3 is here. So what's happening on the left? As I get close to 3 here, the y value gets close to 1. In fact, it's always 1. From the other side, though, x is coming close to what? It's coming close to 1. Both sides have a limit, and both sides have a limit of 1. So this limit exists. How about this one? Limit at 0. Okay, this is a little bit tricky here, so let me do something first. Erase all ink on the side. I think I like that. Okay, we'll take this one. We're talking about getting close to x equals 0. So, first of all, coming from the left, when I get close to where x equals 0, the y value is always a 1. So from the left, the limit is the 1. Remember, we don't actually get there. It's what it's getting close to as we get close to an x value of 0. So the limit left is 1. What about the other side? We're over here, we're getting close to this. As we're getting close, it's still 1 from the right-hand side. It's always 1. Closer I get, it's still a 1. So limit from the right equals 1. So we've got two conditions. We've got a limit on the left, we've got a limit on the right, and not only that, but they're a match. So we've got a limit, period. How about the 3? I guess I did these backwards, sorry. Let's take this one. How about 3? 3 is here. If I'm coming in this direction, I'm getting close to 1, just like we did on the other one. If I'm coming from this direction, I might be hitting higher values at first, and as I get close to 3, I get close to 1. So limit left is 1, limit on the right goes down to 1, and they match, so we've got a limit. There's your answers. 1 both times. Okay, next, we've got some limits to play with here, and I've got a problem here. Let's just move on to the next slide because I've got everything there anyway. Make a note of 42 needs a fix. Okay, slide 42 is sick. So let's take a look. We want the limit as x approaches -2, so we'll look at the -2 right here. From the left, as I get close to this, we're getting close to a 3. So limit from the left equals 3. If I come from the right, it still gets close to a 3. Since they're the same, they both exist and they're the same, then the limit of -2 is a 3. One thing that looks strange, because f of -2 is actually a 1. We don't care. What we care about is, on this curve, what's it getting close to as it gets close to -2? And from this side, what's it getting close to as it approaches from the right side? And both 3's, they exist, they match up, so you've got a limit. How about -2? -2, it says from the left-hand side, oh, I guess I worked out the whole thing. Those match, so you got this. So if you want this, you do that and that. If they both work out and they're the same, then you've got a limit overall. So 3 from the 1. On the second one, these two don't go to the same place, because at 2, it approaches -1 from one side, it approaches 0 from the other side. These two are not the same thing, so we do not have a limit for x equals 2. Okay, let's see. See if I can rewrite this real quickly. We want the limit of f of x as x approaches 2, and what we've got is 10 times x squared minus 4 over x minus 2. So we've got a rational expression here. Now you might be tempted to say, if I put a 2 in there, I'd have 0 in the denominator. It's not going to work at all. However, when you have a rational expression like this, try to simplify it. We can simplify this rational expression. So we keep this limit, and x is approaching 2, and our fraction, the x squared minus 4, factors into x minus 2 times x plus 2 over x minus 2. Now, ignoring the limit just temporarily, because remember, it never actually hits this point, the x minus 2's cancel out. So we can rewrite this as the limit as x approaches 2. And now rewriting this, leaving out the x minus 2's which cancel into 1's, we'll have 10 times x plus 2. Notice that this one, when we multiply it out, is a polynomial. So the good news is we can figure it out real easily. just put the 2 in where the x is, and we've got our limit. 2 in for here gives us 4 times 10, 40. There's our answer. Okay, let's see. Another one that didn't turn out too well. So I'll just rewrite this for you. We need x cubed minus 125 over x minus 5 cubed. And x is approaching 5. Now, similar to the last one, it looks as though if we tried to put 5 in, we'd be in big trouble, because the denominator would be 0, and it isn't going to work for us. However, this numerator can actually be factored. We can factor the numerator because it's a difference of cubes, so I can factor this as x minus 5. And if you're wondering how I get this, you need to tone up on some of your factoring. X squared plus 5x plus 25. That's the numerator. The denominator is x minus 5 cubed. So x minus 5 cancels there, and x approaching 5. And in the denominator, it cancels one of those, so we still have the x minus 5 squared. So what happens? Well, you can do that backwards, see what's on the bottom. That's what we just did. But the denominator approaches 0. I change this limit to the limit of the top over the limit of the bottom. This becomes 0, and we have something over 0, and doesn't give us a limit at all. The limit fails to exist. You could try this one. I'm going to let you do this one. These slides are almost finished. I would think you'd be able to see this. X is approaching -3, and we've got 2x squared plus 5x minus 3 over x plus 3. I'll just give you one hint, and then I'm going to call it quits for the night. The hint is factor the numerator. And with that, we're going to say sayonara for 2.1. Limits, have fun with it. Some of it can be fun, some of it might be frustrating for a while, but work with it. Bring your questions to class. We'll see you next time. Bye-bye.